Okay, Mishler Maths kids, we're going to put some more fun in functions. Today we're going to talk about graphs of polynomial functions. And we're going to identify and describe the important features of graphs of polynomial functions. One of those features is max or min, okay, or maximum or minimum. And do you remember we talked about this before, I think. You know, if you have a quadratic, okay, then it obviously has a max right here, okay? Remember we talked about quadratic functions that go, you know, both of the sides point down and both of the sides point up. And this is a max, okay? And if we have another quadratic function, it goes like this, and curves up, we have a minimum point, okay? Maximum value, minimum point. Well, obviously, if you look at this, this looks like a cubic function. And it is a cubic function, and we have both a max and a min. So we call that a local max and a local min. And we're going to talk about intervals, okay? Let's suppose I choose this interval between here and here. Well, among this interval, or in this interval, okay, this interval here, now forget about this over here for now on the left, and forget about this on the right for now. We're just going to choose this interval right here. And we're going to say, okay, in this interval, this is the lowest point on the interval. And if we make this the a value, or the x value is a, then we can say, okay, suppose I choose x sub 1, and over here I choose x sub 2. Well, what we're saying when we say this is a local minimum is that f at a is the lowest point possible in this whole curve. So whatever x I choose, which is x sub 1, let's suppose I choose x sub 1. This is f at x sub 1. Or I choose x sub 2. This is f at x sub 2. Anyway, anywhere I go on here, I'm going to have a value which is greater than f at a. Okay? And that's what the book is talking about when it says if x doesn't equal a along this interval, then any other x value is going to give you a y value, or f of x, which is going to be greater than f of a. And so that's all that means when we talk about the local min. And the same thing, just the opposite is true with a local maximum. Okay? We're saying that this is, say this is f of a, and this is a. Okay? All we're saying is that all the other x's will give you a result, or an f or a y value, which is going to be less than this maximum or greater than this minimum. So I know it sounds pretty complicated, a lot of talking, but it really is an important concept to understand. And the other thing is interval. I want you to understand the idea of interval. And let me tell you what I mean by that. And okay, again, let's look at another graph. And okay, I'm gonna make just to create a estimate of a graph. And okay, I'm making this up as I go along, folks. So I've got a minimum right here, obviously, and that looks like it's at 1, 2, 3, x equals negative 3. Okay, so x equals negative 3 right here. Okay. And right here, I've got, or up here rather, I've got a maximum, okay? So I got a min here, and a max here. And this one looks like x equals 2. And so the way we describe this, we say that the graph of f of x, and again, this is f of x, the graph of f of x. Okay, so we say that the graph of f of x is increasing from negative infinity oops, I'm sorry. I said that wrong. My bad. It's increasing between positive 2 and negative 3. So the graph of f of x is increasing along this interval here. Okay, between here and here, the graph is going uphill. That's all this is saying, is increasing from negative 3 to 2. Okay, so, and again, this is the interval we're talking about right in here. Okay, forget about the y values for right now. We're just talking about the x values, and the y values are increasing among when we're in between these two x values. All right. So what about decreasing? Okay, it's decreasing if x is less than negative 3 or x is greater than positive 2. So these two intervals described here, and we're talking about from here to here and from here out here, these two intervals here, okay, are the ones that are where it is decreasing. Okay, and I'm hoping you understand what I'm talking about there, because we're going to go on to the next one, and that is we're going to show you an example of what we're talking about. Okay, and not here, we're not. Okay, let me back up here, and all right, I'm going to give you a function. Let's suppose I have the function p of x equals x to the third minus 2x squared minus x plus 2. Okay, that's p of x. Now, I'm going to graph that on a graphing calculator here, and that's what the graph looks like. This is the graph, x to the third minus 2x squared minus x plus 2. So I graph that, and there's my graph. And I'm going to zoom in a little bit here. And zoom, I just go zoom in. Enter, enter. And that doesn't show me quite what I want. So I'm going to go negative 4 to 4. And then negative 2. Let's make that negative 4 to 4. And then graph it. There, I like that a little bit better. And so here's obviously my maximum right here. And so I say second calc. And you see my max right there, number 4. And I want to tell it where to look. So I go enter and enter. So it's going to look in between those two arrows, and then enter, and sure enough, negative 0.2 and positive 2.1. So the coordinates for the max, okay, I have a max at negative 0.2 and 2.1. Those are your x and y values. Okay. Now I have a min as well. And so let's take a look and see where that min is. Again, I go second calc, and this time I hit 3 for minimum. And left boundary somewhere to the left of that minimum point, and right boundary somewhere to the right by hitting enter. And so I'll look in between these two arrows. Okay, and enter. And 1.5 and negative 0.6. So minimum is at 1.5 and negative 0.6. This is the x, and this is the y values. So what does that all mean? For example, if the question is approximate the local minima or maximum, I've done that right now. And I say the local maximum, it has a maximum of 2.1. Oops, sorry. Maximum of 2.1 at x equals negative 0.2. Now, that means that y goes up to 2.1. That's the highest it goes along this interval. And it does that at x equals negative 0.2. And then for this one, I say it has a minimum of 1.5. Excuse me. Minimum of negative 0.6 at x equals 1.5. There we go. So minimum of negative 0.6 at x equals 1.5. And then it says find the intervals among which it is increasing or decreasing. So what that means is, okay, if I'm going to give a crude approximation of this graph. If I look at it again, I can kind of, it goes up here and like that, okay. So, and this goes down a little bit more, of course. Anyway, so I go to where my minimum is at 1.5, okay. I go to where my maximum is at 2.1, and I just divide it up into intervals. How do I know where the intervals are? The intervals are based on my x values. And so it's decreasing between x equals negative 0.2 and 1.5. It is increasing at x is less than negative 0.2 and x is greater than 1.5. So those are the two places where it's increasing. At any rate, we're going to talk a whole lot more about this during class, of course. And next thing we want to talk about is continuity. So continuity simply means one thing, that a polynomial, the graph of a polynomial function is continuous, okay, over the whole graph. And get a different color here. I didn't like that color. So anytime I have a graph of a polynomial function, like that maybe, it's going to be continuous over the whole thing. What that means is that I'm not going to have a place where the graph goes like this, okay, and like that. It's not going to be discontinuous. This graph is discontinuous over this interval. So that's why we don't call this graph continuous. If we have a polynomial graph, or the graph of a polynomial function, then it's going to be continuous over the whole thing. And if that's the case, we have to figure out what the ends of this graph do, okay? And so there we go. So we're going to look at end behavior. End behavior. So the end of each graph, or the polynomial function, the graph, the end is either going to go up or down. Okay? That's what the end of the graph is going to do. They're either both going to go up or they're both going to go down, or one's going to go up, one's going to go down. And so we can actually develop a system for finding out which one it's going to do. And what we need to do is we need to look at the degree of the graph. Because do you remember when we did a quadratic, the degree is 2, and the graph looked like this, or else like this. Remember that? And so okay, let me get my things together here. And so the degree, but then if we look at a third degree, a cubic equation, one side goes down and the other side goes up. Now, the important thing to remember when we're discussing end behavior, it's a little bit different to when we're talking about the intervals and where it's increasing or decreasing over an interval. When we talk about end behavior, we're talking about whether the end of the graph goes up or down. Now, a lot of people get confused like this because if you start on the left and work to your right, it looks like this graph is going up from here, or the end behavior is going up. No, okay? What we're talking about, when we're talking about end behavior, we look at it a little bit differently. We say start in the middle. When we go to the right, does it go up or down? It goes up. When we go to the left, does it go up or down? It goes down, okay? So we look at two things when we look at end behavior. We look at degree, and I did that again. I am so bad about this today. Okay, we look at degree, and the other thing we look at is a lead coefficient. Now, in order to find the lead coefficient, we have to put it in standard form. That means the highest degree exponent first, down to the lowest or the smallest exponent. And so, if the lead coefficient is going to be either positive or negative, okay, the degree is either going to be even or odd. And so there's actually a very neat system, and you're going to have to find that system by doing the project that's in the textbook. And anyway, there's one more thing before you do anything else. I want to show you something on this, and that is, get rid of that. And let's take a look at P of x. Okay, and this is P of x. It's negative x to the third plus da 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 da. So if you look, the lead coefficient is the x to the third, because this one is in standard form. So P of x is negative x to the third. Well, what's the degree? The degree is 3. So it rises on one side and drops on the other. And the lead coefficient is negative. And so it actually rises on the left side and decreases on the right side. And so then let's take a look at the next one. Now, if you look at this, I don't know if you can see this when you with your screen, but the lead coefficient, this is not in standard form. So it's a fourth degree equation, and the lead coefficient is negative 1, negative x to the fourth. So the lead coefficient is negative 1. So that means they both ends decrease or drop. Okay, so the graph points down on both ends. So that's just kind of an idea of what we're looking at when we ask you what to do about the how to describe the end behavior of graphs. Okay, thank you very much. That's it.